This conference will now be recorded.
Okay guys, let us start today's session. So in our last class we have learned some examples where we have proved a function is big O of n square, right? 3 or 4 function we tested and we have proved that along with by learning the rules of properties of the growth rate function. After learning the rules, we have tested some example also in terms of the big O notation, and I'm given one homework also. So this is very easy, very easy. Let us assume f of n. F of n indicates what? Function of n. So f of n is equal to 3 plus 1 by n. This is the function of n they have given. Now, what is the constant here? 3 is the constant here, right? And I have to prove it as big O of 1. That is what I have to prove here. So if I see the constant values here 3 and here it is 1. So we can write here as 3 plus 1 by n, it is less or equal to 4. It is less or equal to 4. But for what values of n? For n greater equal to 1. N greater equal to 1. Now you substitute n value as 1. If you substitute n value is 1, 3 plus 1 it becomes 4, equality holds. If you substitute n value as 2, then it is 1 by n. So that means this part will gradually decremented. 1 by 2 means half. So 3.4 less or equal to 4. If you make the n value as 3, 1 by 3 means it will become 3.3, not even half, not even 3.5. So the more now n value will be incremented, this 1 by n will be decremented. And as a result, this value will be decremented. So now I can say that this 3 plus 1 by n, it is holding for less or equal to 4, holding for all n value greater or equal to 1. And what we have learned, the definition of big O, by definition, what is the definition, sir? 0 less or equal to fn less or equal to cgn. Remember that definition. If it happens, we will say that fn is a big O of gn. So here, so what is the c value here? This what is function of n. C value is becoming what? 4. So c is equal to 4 here. G of n, nothing as such, no, nothing is there. So we can assume that g of n is equal to 1 and n0 is equal to what? N0 is equal to 1. N0 is equal to 1. So now from the definition we know that, sir, if this rule holds fn less or equal to cgn, what we do is that we call fn as a big O of gn. We call fn as a big O of gn. So now what we can say? We can say f of n is equal to big O of gn. Big O of gn is what? 1 for all n greater equal to n0. What is your n0 value here? 1. For all greater equal to n greater equal to 1, where n0, of course, I already have written n greater equal to 1, where n0 is equal to what? 1. That's it, sir. So now let's some example where we can give you the proof of big omega notation. This is with respect to big O. So let's take some example with respect to big omega. So before going for big omega, let's take another very important example, and after that we will move to big omega notation. This is example 4. Example 5. Observe here. Let f of n is equal to So first let me write it, then I will tell you what is this thing. First of all, power. N to the power m. N to the power m minus 1. Gradually decreasing. This is n to the power 1. And then n to the power 0. N to the power 0 means what, guys? 1. So nothing is there. Next, suffix. Am. M minus 1. A1. A0. This is a function of n. Show that f of n is equal to big O of n to the power m, because that is the highest power here. Okay, this is what we have to show. The first activity is, let us assume, let c is equal to, see here all these things are basically constant. This A0, A1, then before that A2, A3, A4, AM minus 1, AM, all these are basically constant. So what I'm doing here, I'm writing let C, which is a constant, that constant is equal to AM plus AM minus 1 plus A1 plus A0. This is what I'm assuming by taking all the constant terms. Okay, so I need one symbol, guys. Wait 1 minute. What happened? Sigma. Okay, so this thing we can write equal to sigma. That means summation of, you know that, summation of ai. We can write this thing as summation of ai. Then I will be varied from where to where, sir? I will be varied from 0 to m, 0 to m. Up to this I will be varied. This is what we can write, sir, from this one. Now, so let me write this thing first, then I will tell you how it is happening. I'm taking this am, which is a constant term. I'm taking this constant term. I'm taking this constant term. This constant term, or rather, okay, no issue. This constant term I'm multiplying with. This is the constant. This is what I'm multiplying with n to the power m. So basically what I'm trying to do is that I'm trying to write this one. The function of n, whatever they have given, that is what I'm trying to write here, nothing else. Plus. So next term will be what? am minus 1 nm minus 1 plus a1n plus a0. So this will be not here, here. It will be what, sir? m minus 1, and this will be nothing here, suffix m minus 1 a1 lastly a0. This is the given, whatever is given, that is what I've written here, nothing else. Exactly the thing that is given in the question, I copy pasted that here, sir. Let me add those dot here. Yeah. Now this thing, the total thing, guys, this total thing, what I can say about this thing will be definitely less or equal to, this will be definitely less or equal to, observe carefully, this will be less or equal to, observe here, I'm writing those constant. What are the constant? You know that am plus am minus 1 plus a1 plus a0. These are the constant, you know that. What is the first one? am. This will be m minus 1. This is a1, this is a0. This is the constant. So observe carefully here, left hand side, the first constant is multiplied with n to the power m. Now on my right hand side also, I'm doing the same activity. That means multiplying the first term with n to the power m. Multiplying the first term with n to the power m. Okay. Now the second term is what? am minus 1. Now on my left hand side, am minus 1 is multiplied with what? N to the power m minus 1. But instead of multiplying n to the power m minus 1. If I again multiply this term, that means the second one, if I again multiply this term with n to the power m, don't you think that it will be a bigger term? Don't you think that just with respect to compare these two part, just compare this part and this part, right hand part will be bigger now, because constant both sides same, am minus 1 same, but here constant is multiplied with n to the power m, here also so same, but here second constant is multiplied with n to the power m minus 1, and here it is multiplied with n to the power m, so this fellow will be bigger now. Yes. Similarly, for all the terms, I'm multiplying with n to the power m only, so automatically it will become a bigger term, sir. Automatically it will become a bigger term. Lastly, yeah, this is what I'm getting, sir, and this is true for all n. This is true for all n greater equal to 1. This is true for all n greater equal to 1. Suppose you take any n value here, whether it is 1 or whether it is 2, and suppose some m value, let it be 3. So 2 to the power 3 means 8. So this constant is multiplied with 8. Here also the constant is multiplied with 8. Here some constant that is multiplied with n, what I said 2, m what I said 3. 3 minus 1 means 2, 2 square 4. Here the second term is multiplied with 4, but here the second term is multiplied with what? Same 8. So don't you think that constant into 8 plus constant into 4 will always be lesser equal to constant into 8 plus constant into 8? Let's say for all n is equal to 1, this relation is going to hold, sir. This relation definitely is going to hold, sir. Now what I can say implies, so what is this fellow actually? What is this fellow actually? See, this fellow is nothing but your fn. This fellow is nothing but your fn. What I can write, fn lesser equal to, now you see here in everywhere n to the power m is there, here, here, next term, next term, next term, next term, next term, everywhere n to the power m is there. Nah? So what I can do, sir, I can take n to the power common. I can take n to the power m common. If you take n to the power m common, what is the thing will be there? Which thing will be there? Sir, first one will be am, then am minus 1, then sir dot dot dot, then a1, then a0. That means basically which thing will be there? This thing will be there. If you take n to the power m as common, and this is nothing but, you know that, sir, addition of constant will be what, guys? Constant only. So this particular part a0 plus a1 dot 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 up to am is nothing but it's a constant, sir. So can I say that this thing is basically equal to n to the power m and this portion is basically equal to what? This summation, na? So what I can write here, into this summation. So this is n to the power m, sir, and this is the thing. That is what I'm getting, sir. Remember, writing this in this fashion doesn't mean fn is equal to this. Writing this in this fashion means this portion is equal to this one, not fn is equal to, no, fn is less or equal to this, where this part is equal to this part. That means now what I can conclude, sir, very simple. F of n is less or equal to, what is this part. F of n is less or equal to this part, sir. Now you observe one thing, guys. This portion is basically function of n, because whatever the m value will be, it is always be function of n, because n is there. And this part is what, sir? This is a constant, basically. This is basically a constant. So then what I can say, suppose for example, this is my number 1. And what is the definition you learned of big O? Now, by definition, already we know that. What is that? 0 less or equal to fn less or equal to cgn less or equal to cgn. What is c? Constant. What is g? It's a function of n. What is f? Function of n. Let it be my number 2. Now what I will do, I will just simply make a comparison. Comparing 1 and 2. What we can say? First I need to identify c. C means constant. Here who is the constant? Sir, this portion is the constant. This portion is the constant. So comparing 1 and 2, what we can write here? C is equal to, that is my constant, is this portion. Is this portion. So C I got, then Gn. What will be Gn, sir? Gn will be equal to function of n, n to the power m, sir. Yes. Gn is equal to n to the power m. Great. What about n0? You said for all n greater equal to 1. So what about n0? N0 is equal to 1. N0 is equal to 1, sir. N0 is equal to 1. Done. Therefore, what is there? Nothing. F of n, hence f of n. It's already proved now. 0 less or equal to fn cgn, proved. Everything is done. Hence fn is equal to, if this relation holds, whenever this relation holds, what you say? Fn is equal to big O of gn. So now fn is equal to big O of gn. Who is your gn, sir? N to the power m. That is my gm. That is my gn, not m, gn. Done, sir. That is what they are asked to prove. Any doubt, students? How it is proved? Fn is equal to big O of a to the power n. Any doubts? Basically same. That highest terminology came na, sir. Even without proof, I can say that fn is equal to n to the power n, because that is the highest power. That theoretically. Now from mathematically, already you have also here you have proved that yes, fn is equal to big O of n to the power n. Any doubt, students? Can I move to the next level? Yeah. So enough. So enough number of example we have practiced to prove a function fn is less or equal to cgn, to prove that this one big O notation, right? Upper bound. Now we will go for some example before we can start. No, this question will not ask in interview, but from your knowledge purpose, you must have that, right? This will definitely never ask in interview. It will never, they will never ask. That is for sure. Okay, na? Yeah. Next, let us go for the next one, sir. Examples of next one, big omega notation. Because actually without giving practice of some of the example, I cannot directly go to that, you know what is called those algorithm analysis. A little bit of practice I definitely have to give. That is what I'm doing here. Example of big omega notation, big omega example. Just same, once we have done that for big O's, or nothing is there now. Only the reverse thing we are going to see. Earlier we have done what? Fn is less or equal to cgn. Now our target will be fn is greater or equal to cgn. Same approach will be there. One minute, guys. Okay. So how can we do that, sir? Same example we were going to take only. Example 1. Let me take that same one. What is this? This one. Three n square plus 4n plus 1. Earlier we proved that it is big O of n square. It can be also proved that it is big omega of n square. Big omega of n square, it can be proved. How we will prove that? Target will be same. What is that? I have to take this as f of n. So let f of n is equal to the given function is equal to, this is the function 3n square plus 4n plus 1. This is the function. Next, remember I have to show what? Fn greater or equal to cgn. So that's very easy now. Why? Sir, this part will definitely be greater or equal to, na? Greater or equal to showing is very easy. This will be definitely greater or equal to 3n square, sir. This will be definitely greater or equal to 3n square. Our left hand side terminology is what? 3n square plus something. And here you are only 3n square. So don't you think that left hand side part will be more than the right hand side, sir? Here nothing like addition of constant and etc, etc. Very easily you can say that 3n square plus 4n plus 1 will always be greater or equal to 3n square. And what is the definition? By definition, what we are having? F of n greater or equal to cgn. That dot you give or don't give, not issue. That's the multiplication sign. Now why we are taking 3? Because I need some constant. And by just looking at this term, I can say that this is 3n square plus some part. Suppose this is x. So 3n square plus x will always be greater than 3n square, na? That's why instead of taking it, thinking about a different constant, keeping it simple, 3n square plus something will be greater or equal to 3n square. Whatever it will be there, that term I have taken here. If it is 7n square plus something, then that will be greater than equal to 7n square. No hard and fast rule, but very easy to decide here. If I take 2, 4, you may answer y2, y4. But if I take 3, not that much difficulty you will face, because this is simple. 3n square plus x will always be greater or equal to 3n square. Clear? Yeah. No hard and fast rule. That's the issue. So fn square greater or equal to cgn. Where is our definition? Yeah. Fn square greater or equal to cgn. That dot I am using here. Here, whatever I've given star, that I'm writing here as dot. Basically, both are multiplication. For all n greater or equal to n0. Then what we are going to call? Sir, fn is equal to big omega of gn. Now you see here what is happening. Which thing will be your c? Sir, 3. Which thing will be your gn? N square. Gn is equal to n square. And lastly, here equality hold on. Equality will be holding. When equality will hold? If I take n value as 1, what is this? 4 plus 1. So here it says greater or equal to, means either greater than or equal to, and if it is possible to hold both, no problem. But remember, my n0, my c and n0 my c and n0 must be a positive value. They cannot be 0 value, sir. So now I can say that c is equal to 3, gn is equal to n square. Equality is not holding, no issue. At least greater or equal to means what? Greater or equal to. Greater than is definitely holding. Na? If you take n value 1, this will become what? 3 plus 4 plus 1, 8. This will become what? 3. Strictly greater than. Now you take any n value, 2, 3, 4. Obviously this term will be greater than, sir. So that means n greater equal to n0. That means n greater equal to 1. Equality I'm not getting, no problem. At least greater than I'm getting. Then ultimately what we will conclude? Hence f of n is equal to sigma, big sigma of n square. Any doubt? Any doubt? Now I hope if I give this second example, you will be able to very easily do that. Same example I will copy paste. This one. Seven n cube plus 5n square plus 6n plus 2 is not anymore big O. Big omega of n cube. So why 3 is taken as constant here and 8 in big O? 8 in big O. In big O, what we have done? We have taken the constant values to take that 8. Here I have taken 8. See, it's as I'm telling you, there is no hard and fast rule. No one is giving you, no one is asking you have to write 8. Suppose you are telling, sir, can I write 9 here? You can write. Sir, can I write 80 here? You can write. Can I ignore here and consider n square? You can do that. but you have to take some value and you have to prove that for that value this is holding. You have to prove that you can take any value, but for that value, there is no restriction. No one is asking you that you have to take the constant summation and you have to assume that. You can, by default you can assume any value, but this relation that it's holding, you have to show that may be less than or equal to some relationship holding is, you have to show that. So that's why we are, what value we should do, sir? There is no algorithm, no rule is there. We just taken this 3 plus 4 plus 1 and taken this 8. Similarly here, this time I have to show what greater than. Again, sir, is there any restriction that I have to write 3 here? Sir, can't I write 2 here? You can write. Can't I write 500 here? You can. If you write 500, there is a possibility that you will not be able to show that this value is greater or equal to this. Suppose you are taking 500 n square. What will happen? N is 1. That means what? 500. Here, n1, 3 plus 4, 8. 8 greater or equal to 500. Not possible. You can definitely take any constant, but the relationship is holding, that we have to show that. Now I'm taking 3n square means you can go for 2, you can go for 1. Clear? Sir, can I take 4n square? Yeah, you can take 4n square also. As long as this relationship is holding, you can take 4n square. That's why this is not the upper bound, na? That's why this notation is not for the upper bound. It's the lower bound. When we have learned this definition, we said that this is the upper bound. Big O is the upper bound. This one is the lower bound. More than that, it's not like that it is the last one. It is not the last one. Now understanding why I have taken 3 there? Yeah. Similarly, second one, what we are supposed to do? This is the Fn. Again, what you will do? Sir, let Fn is equal to this. Now what you have to show? Sir, this value is greater or equal to some constant into n cube. What is that constant? Your choice. You can suggest me, sir, I will take this constant. Take na, no problem. But somehow I have to check it that whether it's working or not. That is what I will check. So I don't know which constant to take. To keep it simple, what I'm doing, I'm simply saying that this value will be definitely. Remaining things I am not sure when it will, whether it will be happening or not. For other constant values, whether it will be happening or not, that I don't know. But I can give you the guarantee, na, sir, this value will be definitely greater or equal to 7n cube. That you can immediately tell, na. 6n cube, 60n cube, whether it will happen or not, you will not able to tell directly. But this one will immediately tell, na, sir, this value will be greater or equal to 7n cube. Aniket, this one will definitely tell, na, sir. And if I ask this is greater or equal to what? One thing will automatically come, sir, definitely greater or equal to 7n cube. Whether 8, 9, 10 or not, that's a different level story. That may be, that may not be, but this one is automatically coming to my mind. That's why I'm writing, sir. Now, remaining things are same. By definition, copy paste, sir. Only thing is the value change. What will be the value this time? 7. What is the value now? N cube. Seven n cube. This is what I have to prove, sir. Done, sir. So this is all about my big omega notation. Only one more left. That is called big theta. Big theta is what? Tight bound. That means both the condition I have to show, sir. It will be bounded above and bounded below. Both the thing I have to show. So let's take an example. Remaining two example also you can try. Same way for the remaining examples of big omega, you take those examples and can try. So now examples of big theta. Examples of big theta. Big omega notations. Big theta, sir. Where is theta, guys? Yes. Examples of big theta notation. Simple. Whatever you learn for big omega and big theta, big sigma, big omega and big O, that too you have to merge now. That means once you have to show less or equal to CGN, on another side you have to show greater or equal to CGN. Very, very easy. Same example, sir. 3n square plus 4n plus 1. Will be what? Big theta of n square. Big theta of n square. So I already have both of the parts separately. Now I have to merge that too. Then automatically it will be done. So first one is what? This is Fn. Let Fn. Now what earlier you have written Fn is equal to 3n square plus 4n plus 1 less or equal to 8n square. Now you may ask, sir, I don't want to write 8. I will ask then what you will write? Sir, I will write 4. Write 4, I don't have any issue. If you really want to write 4, I don't have any issue. But if you write 4, now you'll ask, sir, why you write 4? Why you write 4, sir? Rather than that, if I write 8, I will tell, okay, 3 plus 4 plus 1, 8. That's why I've taken that 8. But you are not supposed to exactly follow this one. Your choice. Some constant I need, sir. That's why I said every time there is no hard and fast rule is there. So 3n square plus 4n plus 1 less or equal to 8n square, and definitely sir greater or equal to 3n square. Isn't it, guys? total value will definitely be greater or equal to 3n squared, sir. Now what we are supposed to do, see the definition of ours. So this what I forget to add. This part will be here in this definition also. Add it, guys. May not be there in your note, just add it. So this is my definition, sir. As per this is the definition. Now put it here. This is what by definition. C1Gn less or equal to Fn less or equal to C2Gn for all n greater or equal to n0, and C1 and C2 are constant, sir. Now you relate. What about your C1? 3. Gn n square less or equal to. What about your Fn? 3n square plus 4n plus 1. C2 8. Gn n square. No, I will not take 8. I will take 4. You take 4, no issue. You take 4, no issue. Clear na? Now what we are going to tell? Hence, what about your C1? 3. Here C1. It should be capital or capital, small, doesn't matter. Some constant. C1 will become what? 3. C2 8. N0 1. Left what? Gn that equal to n squared, sir. That is equal to n square. Done. Hence Fn is equal to big theta of n square. So for other examples also you'll able to show that. Now you have learned how to show this. Big O, big omega, big theta. So try it once with other example also, right? So this is all about our discussion with respect to this asymptotic notations and everything. Now we will see how to calculate the complexity, analysis of an algorithm, sir. Now we have to see analysis of algorithm. File. Save this one first. File, new. Mainly we will first analyze the loops. Analysis of algorithms. Mainly loops. That is analysis of loops. Very easy. Observe here. First of all, when we are going to consider a loop or whatever with a big one complexity, number one, big O of 1. Now as I write now big O of 1, you are not having any issue, because you can understand, oh, big O notation already I have learned. Sir is talking about that one, big O. So when I will say that big O of 1, a particular loop is there whose complexity will be big O of 1. Simple, guys. Suppose you are having a loop like this. For, don't think that loop always means complexity will be, sir, big O of n, big O of n square. No. I'm writing a for loop like this. For I is equal to 1, I less or equal to c, I plus plus. This is my for loop. And most important thing is that consider the following for loop. Most important point here is c is constant. Constant means simple, sir. A loop will rotate for exactly 5 times. Not like a n, where n value will be varied. Sir, maybe 5, maybe 7, maybe 80, maybe 90. No, 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 no. It's not a variable, it's a constant. And inside it, inside the loop also, I'm having some statements which will execute only one time. That means some big O of 1 expressions. Sir, can you give an example of big O of 1 expression? Very simple, guys. Printf ABC, big O of 1. So let us assume inside the loop I am having I is equal to 1, I is equal to I plus 1. One time, big O of 1. So let us assume this is the loop where inside the body everything is having on complexity of order of 1, and here the loop variable, loop condition checking, here c is constant. This is important. By mistake, if you thought c is a variable, complexity will not become order of 1. So that's why c is constant is very, very important. So that means time complexity of a loop is considered as order of 1 if it rotates or runs constant number of time. That means what we can say here, a loop that runs constant number of times is considered as big O of 1. Similarly, we can say that time complexity of a function is considered as, suppose one function is there and someone is asking, tell me what is the complexity. If it is a constant and very much high, then also big O of 1. How much high you can consider, you can consider. But if it is a constant, that's the important one. How much high you want, you can consider, but end of the day it will be a constant now. So that's why time complexity of a function is also considered as order of 1. When, sir? If it doesn't contain any loop, or even contains a loop with order of 1 complexity. So if it doesn't contain any loop, recursion, and call to any other non-constant time function, means what? Suppose you have a function. Suppose you are having a function. This is my main. From here, suppose you are calling a function f1. F1. Now here if1 function you are defining here. And inside f1 you are having only this type of statement. if x greater than 3, do this, else do this. This type of code is there. Suppose here int x is equal to some 4 or 5 something. This type of code is there. Someone is asking, tell me the complexity of f function. Then what you will say? Sir, in f function, every line will be executed how many times? Only one time. Every line will be executed how many times? Only one time. So what is the complexity of this f1 function? Order of 1. No loop is there. Even loop is there, then also it can be order of 1. Suppose f1 is having a loop like this. I is equal to 1, I less or equal to 32768, a big value. Aniket is asking, sir, consider a big value. Okay, I have taken that. If you want more than that, that also I can take. 21, 47, 48, 36, 48. Biggest number in the positive sign of a sign number. This many times my loop will rotate. Someone is asking, oh, tell me the complexity of f1. Tell me the complexity of f1 function. Still big O of 1, sir. Still big O of 1. Now you got the clarity, sir. When I am going to consider the loop, for the loop, most of the cases in a program, loop is the dominance factor. That's why we never go to calculate every line's complexity. We will see where is the loop, where is the loop, what is the loop's complexity. That will become the function's complexity, because that is the thing where function will spend most of the time. Now, do you have any doubt about the order of 1 complexity? Because slowly I will move from here. So if block is executed, else won't work. So how every line is executed once? And every line is executed once means either of them. Suppose today if condition is true, that line will execute. Today if condition is false, else condition is execute. With respect to that, I am telling every line is execute. Not in one run. Maybe in one run if, maybe in other run else. But they will be executed only one, na? They will be definitely executing only one. That is why the complexity will be order of 1. How to determine? Can I move to the next one, sir? With order of 1, any doubt? This is very important. So if you understand order of 1 perfectly, number 2 is order of n, sir. What about order of n? When you will say that a function or a loop is having the complexity as order of n. See here, suppose you are having a loop here, which you wrote like n, and what you are doing, you are having int n here, and that n value you are reading through scanf function. I'm not writing printf function here because I'm not writing the C code. I'm just giving you the clarity. Today n value 10, tomorrow 20, next time 30. And on top of that, see your increment value with a constant, perfect constant, always with 1. Maybe you can keep it 2, maybe you can keep it 3. So you have to remember that time complexity of a loop is considered as order of n if the loop variable is incremented or decremented by a constant amount. That means what I can say, sir. What about order of n? Time complexity of a loop is considered as big O of n. Time complexity of a loop is considered as big O of n if the loop variable is incremented or decremented by a constant amount. Let's take an example for int I is equal to 1. Remember, int I is equal to 1 in this way. Don't think every compiler supports. I'm just writing, that's it. Maybe in some compiler they don't support writing of this one. No way, you declare int I is equal to int I before that for loop, you know that. And I plus equal to c here. I'm not writing 1, it can be 1, 2, 3, 4, 5, 6, anything. And here inside it, let us assume I'm having some big O of 1 expressions. Then what about the complexity of this loop? How many times the loop will rotate? Do you know that? No. N times, sir. N means I don't know. Very. Suppose I write the loop in a different way. I'm making it decremented. I is equal to 1, I greater equal to 1, I minus equal to c. What about the complexity of these two loops? Sir, both are order of n. C positive here. C is a positive integer constant. C is a positive integer constant. So this for loop complexity is big O of n. It's simple, Dia. Acha, non-constant time function means, suppose what happened from f1, guys, I'm giving the explanation of previous one because Dia is asking, sir, what about that non-constant function? Suppose you call f1 function, suddenly f1 called f2, and for f2 complexity is order of n. Let us assume here for loop is there, I is equal to 0, I less or equal to n, I plus plus. What about this n, int n, scanf percentile d ampersand n. Now someone is asking, oh, tell me the complexity of f1. Tell me the complexity of f1. F1, complexity of f1. Now f1 function is actually doing what? F2 calling. Don't you think that, sir, calling F2 here basically means writing the logic of F2. If I do write that logic inside F1, that will be equivalent to calling F2. Agree with me? Writing the logic of F2 copy pasted here in F1, isn't it? It is equivalent to calling F2. Agree with me or not? Now, if you are calling F2 here, what about the complexity of F2? Order of n, and hence complexity of F1 will become what? Hence complexity of F1 will also become what? Order of n. But I said what? F1 complexity will be order of 1 in which cases? Sir, if doesn't contain any loop, or if it contains any loop, loop complexity of order of 1 in that case. If doesn't contain any recursion, or if it is calling a non-constant function. Non-constant means a function which will be constant time. Here what I said here. What I said here. If it doesn't contain any loop, order of 1 definitely. No recursive call, order of 1. And call to any non-constant, here non and here non. That means 2 times not means what? Positive na? Don't call a non-constant function. 2 times not means what? Positive basically. That indicates what? Basically I'm talking about calling a constant time function. So if I'm calling a constant time function, then also my complexity will be what? Constant time. If you are filling with this English word, I said what? Time complexity of a function is considered as order of 1 if it doesn't contain any loop, does not contain any recursion, and does not call to any other non-constant function. By mistake, if it calls any non-constant function like f2 here it is calling a non-constant function, sir, then its complexity is becoming order of n now. If it doesn't contain any call to a non-constant function, okay, its complexity will be order of 1. 100 to 100% clear, or you are still struggling with the terminologies? Is it clear now? Perfectly okay? Super. And any doubt here about the complexity of these two loops, order of n and order of n, both the cases? Any doubt here? So we are having still 3 things pending: order of n square, not only n square, it can be order of n cube, log n, log n. 3 more we will discuss. Today we have discussed 2 things, order of 1 and order of n. Just 3 more: order of log n, log n, and then n square, n cube, n to the power 3, n to the power 4, 5, 6, anything can happen, but how we will determine that I will discuss in our next session tomorrow. And after that we will come back to our bubble shot and modified bubble shot, because this is the reason that's why we are doing this thing. Our ultimate target is time complexity calculation of all the shorting. We have done till now we have done 2 shorting, bubble shot and modified shot. We are not able to move further as because complexity calculation knowledge we are not having, but by tomorrow we will have that, and tomorrow we will calculate the complexity of bubble shot and mass shot, and once done, next we will move to our next sorting algorithm, that is known as selection shot. Thank you guys.